Hello everyone. This video to show you the example for simple harmonic oscillation. Yeah, in the previous video we show the solution format of the solution of the equation of motion of simple harmonic oscillation. And the solution of the simple harmonic oscillation is like this: is a position function, is a amplitude times the cosine omega t plus phi. And also in the previous video, we show once you have position function, what's the velocity function, what's the acceleration function, you can obtain that very easily. You have, okay, because the velocity function, yeah, just doing derivative doing the derivative on the position function with respect to time, and acceleration is doing the derivative of velocity with respect to time. And then after doing this derivation, and you will learn what's the maximum velocity and max acceleration of the simple harmonic oscillation. Okay, maximum velocity and max acceleration, yeah, it relates to your omega and amplitude. Okay. Okay, so and the next one we then will demonstrate one problem. Okay, in previously I say for the position function of the simple harmonic oscillation, yeah, I say the amplitude, yeah, here amplitude and phase constant. Yeah, let me make a color here. Amplitude, which color is better? This one, this one, this one, this one. Which one's better? This one. Yeah, amplitude and phase constant are depends on the initial conditions. Okay, so let's make a practice on this. Okay, let's see how initial condition influence the amplitude and phase constant. Okay, the problem is here. Okay, the problem is here. So it said, okay, this is a mass spring system. The mass is 200 grams, and it's connected to a spring, and the spring force constant is 5 Newton per meter. And we are right now it's moving on horizontal surface, frictionless, and also it say initially the block is displaced 5 centimeters from the equilibrium position and released from rest as in the figure. Okay, so the problem just tell you initially the position of the mass, position of the object is 5 centimeters from its equilibrium position, and also it released from the rest. Okay, that means initial velocity is 0. Okay, so it give you this information and let you to find okay, first of all, what's the period, okay, what's the maximum speed, what's the maximum acceleration, and also express the position, velocity, and acceleration as a function of time in SI units. Okay, that's the first problem. Okay, and the second problem is, yeah, it's the setup is the same. Okay, initial position is the same, but we only change the initial velocity. In the first problem, the initial velocity is 0, but the second problem, if we change the initial velocity, is minus 0.1 meter per second. Will this solution changes? Okay, so let's do this example. So okay, so let me just start. Okay, first of all, you just need to memorize. Memorize. Oh, sorry, what a pen. Okay, we may try to memorize this. Memorize the solution of simple harmonic oscillation. Okay, is x function of time is a times cosine omega t plus phi. Okay, and we need the initial condition to solve the amplitude in phi. Okay, and it gives us the initial position and initial velocity. Okay, and first of all, can we calculate omega? Can we calculate omega? Do you remember what omega is? Omega squared equal to k over m. Yeah, don't forget it. Okay, so omega is do we have information of k and m? I think we have. K, the force constant is 5 Newton per meter, and the mass is 0.2. Okay, so what's the omega square? It's 5, 0.2. So you'll get the omega is equal to 5 and 1 over second. And actually it's radian over second. radian over second. Okay, so we have the omega. So, okay, so the next thing we need to solve is the amplitude and the phase constant. We have two conditions. Okay, the first condition is at the initial condition is x0 is 0.05 meter. Okay, because 5 centimeter is equal to 0.05 meter, and the initial velocity is 0. Okay, so we have a position function. Okay, but the initial condition include the velocity, so we also need the velocity function. So velocity function is just derivative of the position function. So I think it's very easy. Okay. Okay, we got these two. So we put the initial condition into these two functions and get the amplitude and phase constant out. So okay, x0 is equal to 0.05. Okay, put a 0 in this function, you will have a times, put t equals 0 in this function, a times cosine phi. Okay, the other is v0 is 0, and put a 0 in the velocity function is minus omega a and sine phi. Okay, so we can by these two equations we can solve the a and phi out. Okay, which one we should solve first? Okay, we solve the velocity first. Okay, I think this is equation 2. This is equation 1. Okay, from 2 we have minus omega a sine phi equal to 0. Okay, and okay, so that's not very tricky. Okay, omega never be 0, amplitude never be 0. Okay, so the only so what's the sine phi? So this is not 0. This value, the omega is not 0, amplitude is not 0, and times the sine phi equal to 0. So the solution is sine phi is equal to 0. Okay, and sine phi equal to 0. What's the simplest solution for phi? The psi could be lots of value. Okay, for example, sine 2 pi is also 0, right? 2 pi is also 0, right? 2 pi is also 0. 4 pi is also 0, right? But we don't need that complicated solution. Just pick a simplest one. So let's tell you phi is equal to 0. Okay, so with this result, okay, so we can back calculate what is amplitude. So from 1, okay, we will have 0.05 equal to a times cosine 0. Cosine 0 is 1, right? So we will get the answer a is equal to 0.05. Okay, so and then what's our position? What's our position function after all? So our position function is 0.05 times cosine omega is 5t, and phi phase constant, yeah, it's 0. It's very lucky it's 0 in this position. Okay, so what's the problem asking for? What's the problem asking for? Let us see. Okay, maximum speed, maximum acceleration, and also want to get the velocity function and acceleration function. Okay, it's very easy. Okay, so what is Vmax? Okay, what is Vmax? Vmax, to remember that Vmax is omega a. So it's phi times the amplitude, 0.05. Oh, so it's 0.25. And what is A max? A max is equal to omega square A. So that's 5 squared times 0.05. So it's 1.25. Okay, so that's a maximum velocity, maximum acceleration under this initial condition. And finally, he wants us to list all the function, all the position function and velocity function and acceleration function. Okay, so the velocity function, yeah, it's very simple. It's minus omega a, so minus 0.25 sine 5t. And what's the acceleration? Minus 1.25. Okay, so minus omega square a. Yeah, just equal to a max, right? So it's also cosine 5t. Okay, I think that's all the answer. What else? Find the period. We forgot the period. Okay, what's the period? Period equal to period. Okay, period. In the previous video, I said angular frequency has a relationship with the period. Do you remember that? Omega times the period equal to 2 pi. So we have omega is equal to 5. So what's the period? The period equals to 2 pi over 5. Okay, and what's the answer? 2 pi 6.28 divided by 5 1.256 1.256 and the unit is second. Okay, that's all the problem for the first problem. Okay, so and what's the next one? The next one is a change in initial condition. Okay, a change in initial condition. Yeah, the initial position doesn't change, but it changes initial velocity to minus 0.1. Will this answer changes? Some change, some doesn't. So some change, some don't. Okay, and let's see what will change. Okay, first of all, we still have to use this. Okay, so I'm just make copy and sorry. Okay, just you have to use this again. Yeah, it's very hard to control this. Okay, so is that we change the initial condition? Okay, so what's the new initial condition? The new initial condition is, what's the new initial condition? Okay, 0 is still the same, 0.05. But the initial velocity change, it becomes a minus 0.01 or 0.1. 0.1 minus 0.1. Okay, so first of all, does the omega change? No, omega doesn't change because omega is only relate to your force constant and mass, right? Omega squared equal to k over m. So omega only relates to your mass and force constant of the spring. So if the spring doesn't change, the mass doesn't change, your omega is still the same. Okay, so omega is still 5. So omega doesn't change. Okay. So, okay, let's start with, let's put initial condition in. Okay, x0 is equal to 0.05. Okay, put the 0 in the position function. 0 put in a times is 0, so it's equal to cosine phi. Okay, and so the velocity at 0 point, it's become minus 0.1, which is equal to, let's see, 0 here, so minus omega a and sine phi. Okay, did something wrong here? No. Oh, okay. So we have these two equation. Okay, so we let that 1 divided by 2, and what will happen? 1 divided by 2, I will have 0.05 minus 0.1. So and minus omega 1 and sine phi and cosine phi. Okay, so can we get the information from here? Omega is equal 5. So, and both sides has a negative sign, so cancel out. And okay, but furthermore, okay, so it is 5 here. So, okay, 0.05 divided by 0.1. Okay, equal to 1 over 5 and sine phi cosine phi. So what will we have? Okay, it's times both sides times 5, so it's 0.25. 0.25. So you will have 2.5 equal to sine phi cosine phi. and it's tell you tangent phi is equal to 1 over 2.5. Okay, from this equation, you can get the phi out. Okay, so that's why you need the engineering calculator or engineer calculator. Okay, 1 minus 2 divided by 2.5. And what is, you use the arctangent. Yeah, arctangent. So arctangent, okay, you will get the phi is equal to, be careful for unit, because I'm not sure your calculator is in degree or in radian. Be careful for your calculator, because I'm not sure. My calculator, the phi is in degree, but but maybe some calculator the angle is in radian. So be careful with your calculator, because I'm not sure. Mine is degree. Okay, I'll get the phi is equal to 21.8 degree. Okay, but I want to translate to radian. Okay, because I said that we like to use radian in the sign here, in the stuff in the sine cosine, we like to use radian. Okay, so we convert it to radian. So how to convert the radian? So 180 degree is a pi radian. So I'm right now I'm 21.8 degree. What is my radian now? So my radian is okay, 21.8 times 3.14 divided by 180. So is 0.38. Okay, it's radian. Be careful the units here. Okay, radian degree. Okay, and also be careful your calculator. Okay, it's degree or radian. Be careful. Okay, so so I get the phi is equal to 0.38 radian. Okay, radian. Okay, we get a phase constant, and then we go use information going back to solve the A. Okay, so what is A? Yeah, amplitude change. Very strange. Very amplitude change. Okay, amplitude A times cosine. Okay, 21.8 degrees equal to 0.05, which give you the A. What is value of A? So cosine 28.1. 0.05. So 0.054. Okay, 0.054. Okay. And so we finally got our position function. Okay, under this initial condition, the position function is 0.054 and times cosine, omega is 5 and t, and plus 0.3a radian. Okay, so we have omega is 5, right? Omega is 5, and amplitude we already know. So what's the Vmax? Yeah, Vmax change, Amax also changes. Okay, and the period doesn't change because omega is the same, so the period doesn't change. Okay, but Vmax and Amax is changing, and Vmax is it's omega times amplitude. So, and Amax omega squared times amplitude. So omega is 5 and times the amplitude, and Amax is 5 squared times the amplitude. Okay. So what's the value? What's the answer? Sure, the answer here. Okay, maybe I draw here. 5 times 0.054. Okay, it's 0 to 7, and times 5 is 1.35. Okay, and finally, what's the velocity function and acceleration function? Yep, I think it's very easy. Okay, so it's minus, Vmax is 0.727, and it's sorry, it's sine. It's sine. Yeah, and inside the sine function the same, and the acceleration. Yeah, same A max. Yeah, times the cosine is minus omega squared times A, right? So it's A max. So it's 5t plus 0.38. Okay. So we just let you know with a different initial condition, we will have different position function. Okay, so let's using the let you practice using the initial condition to solve the solution of the simple harmonic oscillation. Yeah, I think in engineering maybe next year, yeah, you have solve lots of initial condition problem. Yeah, in engineering mathematics. Okay, so I will stop the video here, and see you in the next video. Okay, and in the next part, we are going to use the energy perspective to study the simple harmonic oscillation. Because at the very beginning I said we have two perspectives to study simple harmonic oscillation. One is using equation of motion, yes, like this, using equation of motion, and the other is using the energy perspective, using energy conservation to study simple harmonic oscillation. They are both very important. Okay, so that's our video here, and see you in next video. Bye bye. Where's the stop here?